Ever wished you could build a computer, but like instead of silicon chips and wires, it's all, light. And not just any light, light that's like bending the rules, doing its own quantum thing.
Yeah, like harnessing the strangeness of quantum mechanics to compute.
Exactly. And that's what we're diving into today, this wild paper about using photons, those tiny little particles of light, to build something called continuous variable quantum computing, or CVQC for short. Catchy, right?
Definitely rolls off the tongue. But it's not just about the cool factor. This CVQC stuff could be huge for simulating like really complex physics problems, things even our best supercomputers choke on right now.
Okay, so we're talking about simulating quantum systems. We've touched on this before, but just to bring everyone up to speed, why is this such a big deal?
Imagine trying to understand a hurricane, right? But instead of fancy weather satellites, all you've got is one of those little toy windmills.
I'm picturing it, yeah.
Classical computers, even the super-powered ones, they're kind of like that toy windmill when it comes to the quantum world. They just can't fully grasp how particles behave at that level. It's like they're speaking different languages.
Okay, so we need a translator, something that can bridge that gap between our classical world and the quantum one.
Exactly. And that's where quantum computers come in. They have the potential to be like super-powered quantum microscopes, letting us finally see the nitty-gritty details of these systems.
And that's where this whole quantum field theory thing comes in, right?
Yeah. Right. Quantum field theory, it's like the rule book for how particles interact at the most fundamental level. It's the real deal. Problem is, those rules, they're written in a language that's really, really hard to translate with our current computers.
So we need a new kind of computer, one that can actually speak quantum fluently. And CVQC might be it.
It might be. It's definitely showing a lot of promise.
So quantum field theory, it's important. It's the foundation for so much of modern physics. But can you give us a concrete example of why simulating this is so hard for classical computers?
Think about the strong force, the thing that holds the nucleus of an atom together. Now imagine trying to calculate every single interaction between particles through this force using only classical computers. It would take, well, practically forever. The computational power needed is just mind-boggling. But CVQC, it offers a completely new way of approaching these calculations. It's like trading your old abacus for a supercomputer.
Okay, so classical computers, they're kind of stuck in the slow lane when it comes to this quantum stuff. And CVQC might be the jump to light speed, so to speak. But how does it actually work? What's under the hood that makes it so different?
You know how in the old days we had records, those vinyl things?
Yeah, I've seen pictures at least.
Okay, so imagine you're listening to a song on a record player, right? That's kind of like a classical computer representing the music as a continuous groove. But then you have digital music stored as zeros and ones. That's more like a traditional quantum computer, breaking things down into these discrete bits.
Chopping up the quantum world into little digital chunks.
Right, but the quantum world, it's not chunky, it's smooth, it's continuous, like that groove on a record.
Okay, I'm with you.
So CVQC, it's like, wait a minute, why are we forcing these bits onto something that's natural continuous? Let's embrace that smoothness.
I like where this is going.
And that's where quo modes come in. Instead of bits, it's like, think dimmer switches.
Dimmer switches, like how bright the lights are.
Exactly. A dimmer switch gives you a range, not just on or off. And CVQC can tweak these properties of light, how intense it is, its phase, to store information in that continuous way. It's not just a 0 or a 1, it's the whole spectrum in between.
That's so cool. So instead of bits, it's like dimming levels.
You got it.
This is blowing my mind a little. But you mentioned earlier, even building these CVQC computers is a whole other challenge, right? Something about non-Gaussian operations being tricky.
Yeah, that's the catch.
Like-
Think of it like, to build a house, you need tools, right? Hammers, saws, the whole shebang.
Yeah.
Non-Gaussian operations, they're like specialized tools in your quantum building set. They let you manipulate those continuous variables in really precise ways that you need for the complex stuff.
But they're not just lying around, easy to grab.
Not at all. It's more like you got to craft them yourself, and it's really difficult.
Yeah.
But this is where this paper gets really interesting.
They figured it out.
They found a way. It's kind of wild, actually. They're using this combination of measurement-based quantum computing and machine learning. It's like, imagine teaching a robot to build those specialized tools by letting it try things out, see what works, and learn as it goes.
So they're basically training their CVQC system to build the tools it needs on its own.
That's the gist. And they've gotten some impressive results so far.
So they've got the system, they're making the tools, time to put it to the test, see what this thing can actually do.
That's exactly what they did.
All right, so they've built their CVQC system, got the tools, the non-Gaussian operations ready to go. But how do you actually test this thing? Where do you even start?
Well, you don't exactly jump straight to simulating the entire universe, right?
Probably a good call.
They started with something a bit more manageable, but still a huge challenge, simulating how a single quantum particle behaves under different conditions.
Okay, so like a testing ground for their quantum computer. What kind of conditions are we talking about here?
Imagine a skateboarder in a skate park, but instead of ramps and half pipes, it's this invisible energy landscape called a potential.
Okay, I'm kind of visualizing it.
These potentials, they govern how the particle moves, whether it's trapped, free to roam, or even does something wild like quantum tunneling.
Quantum tunneling. Okay, now you got my attention.
Mhm.
What kind of energy landscapes did they use for their tests?
They use 3 different ones, each with a unique shape that dictates the particle's behavior. They've got these fun names like the quartic potential, which looks kind of like the bottom of a champagne bottle. You've got the Koch potential, which is a smooth curve, like a hammock. And then there's the W potential, which, well, it resembles a W.
Catchy. So 3 different courses for their quantum particle to run.
Exactly. And the W potential, that one's particularly interesting. It forces the particle to tunnel, basically, pass through an energy barrier that, according to classical physics, it shouldn't be able to. It's like walking through a wall.
Okay, that's just straight up bizarre. I love it. But how do they even begin to calculate something like that? Even on a quantum computer, these simulations have got to be incredibly complex.
Oh, they absolutely are. To handle it, they use a technique called trotterization. Basically, they break down the simulation into smaller, more manageable steps. Think of it like, instead of planning a whole road trip at once, you break it down into smaller segments, mile by mile. Makes it easier to digest.
So they're giving their quantum computer bite-sized chunks of the simulation to chew on.
Exactly. And to actually apply the effects of these potentials, the shape of that energy landscape, they create a special quantum state within their CVQC system. They call it the evolver state. And this state acts like a custom-made tool that modifies the simulated particle according to the chosen potential.
So like for each of those skate park ramps, they design a special tool to make sure the particle rides it correctly.
You got it. And here's where it gets even more interesting. They use machine learning to prepare this evolver state. So the system actually learns how to best simulate each potential. It's like giving their quantum computer a crash course in skate park design.
This is wild. They're using machine learning to train their quantum computer to simulate quantum mechanics. What were the results? Did it actually work?
The results were really impressive, especially for the W potential, the one with that tunneling effect. The CVQC simulations, they closely matched the exact calculations done on a classical computer, but with the potential for way better efficiency as the systems get more complex.
Meaning their system accurately captured those bizarre quantum effects, those particles teleporting through walls. So it actually works. This is huge, right?
Right.
We're talking about simulating things that were basically impossible before.
This is just the beginning, and that's what makes this research so exciting. It's a glimpse into the future of what might be possible with CVQC. There's still a ton to explore, but if this approach delivers on its promise, we could be on the edge of a whole new era in how we study and understand the universe at its tiniest level.
From photons and skate parks to the fundamental fabric of reality, it's been quite a ride. That's it for this deep dive, everyone. Thanks for joining us, and keep those brain cells buzzing. You never know what we'll be unraveling next time.